Dear all, good morning. Welcome to the fourth day of the conference. Thanks that you are with us. And today the chairman of the first two sessions is Professor Takeji Takui from Osaka City University. Yeah, please, we can actually start.
Okay, can I start now?
Yes, please.
Okay, here the Takeji Takui is here from Osaka. I'm going to chair the morning session in Moscow time. And the first speaker is going to be Martin from University of New Mexico. You already checked your image? You can start now. Anyway,
okay.
The floor is yours.
Thank you very much.
Okay.
I'd like to thank all the co-chairs and the organizing committee for the invitation. It's been a difficult time throughout the world during the pandemic, and it's great to bring this group of scientists together under these circumstances to share collectively our work. So thank you very much. Okay, can everybody see the screen? Fantastic. I want to talk about three stories today that detail various aspects of spin-dependent delocalization and photoinduced ground state electron spin polarization. Much of this work is done in collaboration with Professor David Schultz, who gave a talk yesterday, or yeah, if that's correct, yesterday, Moscow time, at North Carolina State University. This work has been supported dominantly by the United States National Science Foundation and the United States Department of Energy. So what we've been focusing on in our work is donor acceptor biradical systems and how can they be used to garner a tremendous amount of information about various ground and excited state processes. The general constructs that we've used is this sort of ground state biradical arrangement. And this is a zinc tridentate complex that's bound to a S=1 triplet spin ligand. This is a semiquinone. We can put any bridge fragment between this donor semiquinone and this acceptor radical fragment, nitronal nitroxide, that's synthetically viable, shown here as a phenylene bridge. We also have excited state triradicals that are built on this same concept. And so this semiquinone bridge nitronal nitroxide fragment is shown here. But in the ground state, this is a catechol. When we photoexcite these, we transfer an electron from the catechol with essentially unit spin to an acceptor fragment, a diimine, to create an excited state triradical fragment. The beauty of this is that the exchange interaction between the two radicals in the excited state is effectively analogous to what we've studied in detail in the ground state. So there's a transferable property relationship going on there. What we've also done is used these ground state biradicals with various bridges to correlate magnetic exchange with conductance. This is work that was recently published in Chemical Science. We've executed excited state lifetime control with this fragment as a function of the bridge, which modulates the exchange interaction between these two radical species, and shown that these have a power law dependence on the control of the excited state lifetimes. This was published recently in Journal of the American Chemical Society in 2019. And we recently published work in 2021, again in JAX, where we've developed, using the same type of framework, ground state spin polarization control. And I'll end with a new twist on how we've been able to execute this in our molecular systems. But first, I want to talk about nanoscale electron correlation. This is some older work that we did, but I want to use this as an entree to some new studies that we've been working on. But we have a cobalt 3 metal ion here. So this is low spin D6. This is bound to 2 axial pyridines, a semiquinone and a catacholate ligand. And this complex is elaborated by having 2 nitrile nitroxide radicals that are attached to the dioxylanes. We've been able to separate these radicals even further by putting spacers between the dioxylene and the nitrile nitroxide. The idea here is to determine can spin-dependent delocalization in these systems, and that is, can this mixed valence system undergo a high degree of spin delocalization to couple the 2 peripheral radical spins in these complexes. In complex 2 with the phenylene spacer, these spins are separated by 22 angstroms. And so if there was not a significant amount of valence delocalization, one would expect to have an exchange interaction between a peripheral nitrile nitroxide and a semiquinone, whereas the nitrile nitroxide on this fragment would be virtually uncoupled from the other 2 spins. Not sure why it's taking a long time for me to change slides. Okay. So we looked at optical probes of this valence delocalization, and there are very low energy intervalence type excitations at 3,500 nanometers in both of these complexes, complex 1 and 2. These are shown here. These are dipole allowed U to G excitations. These complexes possess planar cobalt dioxylene cores. We hypothesized that these would have class 3 valence delocalization. If that's true, the ground state should be quartets. And that's based on the presence of these low energy U to G excitations. Time-dependent DFT is in good agreement with the experiment. It predicts that same transition at 3,700 wave numbers. This should be compared with 3,500 wave numbers observed. This quartet A1U ground state for these species is susceptible to a distorting force. All right, this is a pseudo-Jahn-Teller distortion, and this is the force constants that contribute, the matrix elements of the force constant that contribute to the vibronic force constant. And if you go through the group theory here, simply that the ground state and the excited state are coupled by a vibration of BU symmetry, and that's shown here. And this distorting force, this pseudo-Jahn-Teller effect, can serve as a driving force to localize the spin on one half of the molecule. So in one instance, you have a pseudo-Jahn-Teller type driving force for spin localization, and the planar nature of the molecule engenders a large degree of spin delocalization. The question is, which one of these, the spin delocalization of the pseudo-Jahn-Teller effect, is going to win out here? So what we see in complex 1 is this indeed has a quartet ground state, supporting the idea of a large degree of valence delocalization between the semiquinone and the catacholate ligands in this dioxin fragment that would serve to couple the 2 peripheral nitrile nitroxide radicals strongly. We set up a simple Heisenberg-Dirac van Vleck model to understand this with 2 J values between the semiquinone and the nitrile nitroxide. This would be a stronger J in a localized limit. And then between this semiquinone and the distal nitrile nitroxide, that was a second magnetic exchange interaction. And the idea is that in this complex, we expect the exchange interaction to be less because these electrons are farther apart, these spins are farther apart, that the ratio of these J values gives you some kind of an idea of the degree of valence delocalization. If they're very different, that's a localized structure, especially particularly if this exchange coupling constant tends towards 0. And when they become equivalent, this would be a harbinger of the extreme limit of class 3 valence delocalization. And what we observe here is, again, ferromagnetic exchange, but with the remarkable relationship that the two J values are equivalent. It's ferromagnetically coupled, it's a quartet, and the J value in using a negative 2J S1.S2 Hamiltonian or negative 2J formalism is 234 wave numbers. Okay, so we move forward to looking at a spin-dependent delocalization or organic double exchange model. And these are the eigenstates shown here in the energy diagram. We took the experimental value for the low energy intervalence band as a function of the magnetic exchange coupling that we determined experimentally. And we're able to confirm here that indeed what's actually going on is you have a large degree of valence delocalization in the dioxylene that couples radicals that are spatially distant by 2.2 nanometers. So you have nanometer type electron correlation that's promoted by spin-dependent delocalization. Now, in the second situation here, what we did is we decided, well, that's an awfully strong interaction over long distances. What happens if we take that paramagnetic core out and make a diamagnetic core? So here, this is a ruthenium 3 species. And again, you have this dioxylene fragment where one is formally a cataclate and the other is formally a semiquinone, but it couples with the ruthenium spin to give you a diamagnetic core. And now you have these paramagnetic spins that are at a long distance away from one another. And do they couple? And if they do, what is the mechanism of their coupling? What's interesting in the structure of both of these molecules is they have a chelate ring folding distortion. And these are radicals here separated by about 13 angstroms. And that chelate ring folding distortion is, again, indicative of a bibronically induced pseudo-Jahn-Teller distortion. This allows us to develop deep insight into long-range electron correlation, things like carrier-mediated ferromagnetism, and particularly spin polarization in electronic ground states, a quantum information science type application. The EPR spectra of this provides strong evidence for a triplet. So those spins are coupled over 13 angstroms. Electronic absorption and MCD spectroscopy support that same triplet ground state assignment. And the idea here is that we have a situation where we have spins that are very far apart, and how are they coupled? And so this is a picture of what we believe is going on here. These are the relevant frontier molecular orbitals. These are the relevant orbital energies and orbital occupation in the core. There's a low energy AG to B2G excitation that we calculate at about 0.33 electron volts. Again, if we look at the vibronic force constant for a pseudo-Jahn-Teller distortion and determine the symmetry requirements for this matrix element of the force constant, what we determine is vibronically active modes that will distort this molecule and couple the ground state to the low energy excited state are modes of B2G symmetry. In the planar geometry, you find that this is unstable because the molecule is distorted, but it's a low frequency mode at 88 wave numbers. That low frequency coupled with a strong F0I matrix element for the vibronic force constant and a low energy excitation effectively mixes the A1G ground state into the low-lying B2G excited state. That B2G excited state is analogous to what we looked at in the cobalt systems. This is a delocalized excited state, and it's having unpaired spin density in an excited state that admixes into the ground state via the pseudo-Jahn-Teller effect that allows for extreme coupling of spins over nanoscale distances. So we have open shell ruthenium character that's admixed into the ground state via a pseudo-Jahn-Teller effect. Finally, I want to talk about photogeneration of multi-spin exchange coupled qubits. A lot of this work was detailed just last year, or just in Nature Reviews Chemistry. What we're doing here is taking that second construct, okay, that has this excited state tri-radical character, what we do is we take, and again, in the ground state, this is a diamagnetic ground state. This is a cataclylate, and this is just a diimine. So we photoexcite in this doublet ground state into a sing doublet excited state configuration. Right, that's a tri-radical configuration in the excited state. And this rapidly relaxes to this trip doublet configuration. All right, and these states are both doublets and they're admixed. We've worked out the admixture from a detailed spectroscopic study of these systems. And this is a case for ferromagnetic coupling between the semiquinone and the distal nitronyl nitroxide, where you have a quartet state being lowest in energy. If you engender a bridge fragment that has meta connectivity through a phenylene, you get antiferromagnetic coupling. What that does is reverses the doublet T1 and quartet T1 state, so that a doublet state is therefore lowest. And so what was happening is you photoexcite from the ground state into the first doublet. You have rapid internal conversion to the doublet T1 state, and you can use time-resolved EPR spectroscopy to effectively determine the J values in these excited states between these two species. And this is called the reverse quartet mechanism. And when you have antiferromagnetic coupling with the doublet state being lowest, one expects to observe emissive EPR intensity in the time-resolved EPR spectra. If you have ferromagnetic coupling with the quartet T1 being lowest in energy, you would expect to see absorptive EPR intensity in a time-resolved EPR spectrum. So essentially, time-resolved EPR has been a technique that's been used to determine excited state exchange interactions. Well, what we did is we looked at two species that both have antiferromagnetic coupling because the semiquinone and the nitronyl nitroxide are meta-connected to a phenylene bridge. The first complex just has a simple phenylene bridge, but the second one is augmented by a methyl group that torques this phenylene bridge out of plane and reduces the coupling between these two radicals. We measured the exchange coupling in the ground state of the analogous biradical complex, and it's about 10-fold less than the antiferromagnetic exchange that is meta through a phenylene. They're both antiferromagnetically coupled. The reverse quartet mechanism would predict that one would have emissive electron spin polarization in the time-resolved EPR spectra for both. So how does this reduction in the exchange interaction in the excited state affect the ground state spin polarization? Well, what we have here is we're going to change the sign of the ground state spin polarization by changing the exchange interaction. Effectively, what's happening is we're photoexciting from the ground state into this doublet T1 state. This is the quartet state that I showed you earlier. And this type of interaction with a quartet above the T2 should yield emissive spin polarization. But in order to explain why we have absorptive spin polarization in one of these molecules, we had to invoke the presence of a dark state, a quartet state that's localized on the radical fragment. This came from coupled cluster calculations, a prediction of its energy, but we have observed its doublet counterpart by optical spectroscopy when we've taken away the diimine that does not allow any type of ligand-to-ligand charge transfer excitation. So we can actually see the doublet spectroscopically. The quartet is predicted by coupled cluster calculations. So depending on whether this doublet T1 state mixes with its quartet counterpart or a quartet dark state, which one dominates determines the sign of the spin polarization. And that's shown here. So if I have weak coupling, antiferromagnetic, essentially the quartet doublet splitting is very small. This interaction dominates and one observes emissive spin polarization. However, if the exchange interaction is very large, we can have no mixing between the doublet T1 and its quartet counterpart, and that should give you effectively no ground state spin polarization. but this ground state spin polarization is indeed turned on by admixture with the localized nitronyl nitroxide quartet, leading to absorptive spin polarization. In a nutshell, what we can do is photoexcite and go through this photoexcite cycle, and in hundreds of picoseconds generate ground state spin polarization, which is orders of magnitude faster than you can do this with a microwave or a radio frequency pulse. And this spin polarization lasts orders of magnitude longer than the time it took to generate. So it lasts on the order of microseconds. So it's a new way that we envision to generate spin polarized ground states for further manipulation by magnetic resonance techniques. In summary, I showed you examples of valence delocalization and organic double exchange. We talked about excited state delocalization and vibronic coupling induced magnetic exchange in systems that have radicals separated by greater than a nanometer. And finally, we talked about a new area of work that Dave Schultz and I are doing in terms of optical generation and control of ground state, excited state, ground state, electron spin polarization. This is my group. I have to thank them, and I want to leave you with a view of Albuquerque, New Mexico, in case you haven't been there. Thank you, and I'm happy to take any questions you might have.
Okay, thank you very much, Martin. Thank you for keeping your time. So we can accept a couple of questions. Okay, Sergey.
In for one of your objects, you used EPR, the CW EPR and MCD technique to confirm that a triplet state is a ground state.
Yes.
So there was one slide. And can you tell a few more words about how do you use EPR to confirm it? Is it the temperature dependent measurements, or you have somehow simulated the spectrum? So
yeah, the spectrum's been simulated, and this is a Hatfield G=4 transition, which is characteristic of spin triplets. And furthermore, we also know it's a triplet from the temperature dependence of the magnetic circular dichroism. I don't show that here, and the fact that in this system, the only mechanism that's going to yield magnetic circular dichroism activity, it won't come from a free radical because you have to have spin orbit coupling. So there's multiple lines of evidence. One, it's typically the G=4, which is a harbinger of a triplet ground state, the temperature dependence of the magnetic circular dichroism, and the fact that we have excited state spin orbit coupling that's mixed in through the mechanism that we, I think I showed here, this mechanism mixes in metal ion character spin orbit coupling, turning on the MCD activity. Thank you.
thank you.
Okay, so any other questions? We can accept one more question. Okay, I can ask a very basic question. So you talk about Bavaric, I mean the program, pseudo-Yantera effect. And can you tell us about the magnitude of nuclear displacement? For example, vibrational mode would be to D. How big nuclear displacement?
I don't remember exactly what the displacement is.
Okay.
But what I can say is, of course, you get a greater displacement with the lower frequency mode. Okay. And so what you really want to have to turn these on are very low frequency modes. They're going to have very large amplitudes. Okay. And a typical 88 wave number mode, that's a mode where these ligands are flapping up and down, leads to a very large displacement and large coupling of that excited state into the ground state. Yes.
I see. It's very interesting. Okay.
It's the only example I know like that. And thank you very much.
Okay. Thank you very much, Martin.
Welcome.
So let's move on to the next speaker. Kitagawa Sensei from Osaka University is going to tell us about a theoretical study. Okay, Kitagawa Sensei.
Thank you very much. Thank you very much, Takui Sensei. And first of all, I would like to thank the organizers for giving me this nice opportunity to introduce my recent work here under such a difficult condition of the COVID-19. I'm Kitagawa from Osaka University, and I would like to share my slide. Can you see this slide? Okay. Okay. And I'm Kitagawa from Osaka University, and today I would like to talk about theoretical study on relationship between spin states and electron conductivities of extant metal atom chains. I would like to start with the topic about miniaturization of silicon devices. As you know, silicon devices recently have been getting smaller and smaller. For example, this is a recent Macintosh, Mac Pro, and you already know that the recent computers, personal computers, have a potential as comparable to the supercomputers in, for example, a couple of decades before. And there are several merits of miniaturization. And first one is the increase of the speed and increase of the information density, and of course the reduction of the electric power. And this figure excuse me. Okay. This figure shows the relationship between area and the size of the semiconductor. As you can see, the size of semiconductor getting smaller and smaller. And I was really surprised that okay, oh. I was really surprised that the recent paper reported that IBM successfully made 2 nanometer semiconductors. I was really surprised because it is very small and comparable to the molecular size. This is the STM image of single IC chip. This is the illustration of the single IC chip, and this is the STM image. And this is the enlarged view. As you can see, a single transistor, the width of the single transistor is about 8 nanometers. For example, the diameter of virus is about 100 nanometers. So nowadays, a single transistor is much smaller than the virus. And one pitch of DNA is about 3.4 nanometers. So the size of single conductor is comparable to the DNA size or molecular size. And actually, a size of some functional metal complexes become comparable to the single transistor. This is a one-dimensional nickel complex reported by Professor Peng in National Taiwan University. This complex involves 11 nickel ions, and the length of this chain complex is about 2.8 nanometers. So as you can see, the size is comparable to the single transistor. And this one-dimensional metal complex is called extended metal atom chains, and they are considered to be a possible candidate for the molecular wire. I think that this Emax, Emax is an extended metal atomic chain. These Emax also have a great potential for the molecular devices. For example, if we can change the electroconductivity by the external field, this molecule will be act as a single molecular transistor. To my best knowledge, the first proposal of the single molecular device is given by Ratner and Walkers in 1974. They proposed this molecule. This molecule consists of 2 sides. By using the homothermal energy gap between this side and this side, Ratner and Walkers reported that this molecule will show the property of the molecular diode. I think this is the first report about it. This is just a theoretical one, but the first report about the single molecular devices. After that, for example, Professor Smalley and Walkers reported that the single wall carbon nanotube show the quantum wire property. As you can see, the single wall carbon nanotube show the quantized transportation. So this can be considered to be a molecular wire. But we want to make a computer, or we would like to compute something, we need a transistor. The word transistor consists of two words, transfer and register. Of course, transfer means on and register means off. So we need on-off switch in the molecule. So the question is how we can realize on-off switch in the molecule. For example, Professor Yoshizawa in Kyushu University proposed an on-off switch by using a bond breaking of diareacenes in the case of this structure off and this structure on. Actually, this would be the molecular switch, but it needs a large change in the structure. So in my opinion, such large structural change would not so much preferable in the molecular switch for the practical use. On the other hand, Professor Ruiz and co-workers reported that this least cobalt complex shows molecular act as a molecular switch, a molecular transistor. For example, in case of the low spin, this shows this is IV characteristics of this cobalt complex. In the case of the low spin state, it shows a lower conductivity, and in the case of the high spin, it shows a higher conductivity. And these spin states can be changed by the irradiation of the light. So Professor Rhodes reported this would act as a molecular switch. And very recently, Professor Rubin and co-worker reported that single molecular magnets on the carbon nanotube will be used as a quantum bit and useful for the quantum computing. I'm not sure about this is really or not, but I would like to say that molecular conductors with localized spins are promising candidates for the molecular transistor. So I would like to focus on the property of the molecular transistor. In my presentation, I would like to focus on the one-dimensional nickel Emacs, as shown here. These complexes are reported by Professor Peng in National Taiwan University. These are tri-nickel complex and these are pentanickel complex. Very interestingly, nickel ions in the inner part of the complex is a low spin, and the two nickel ions at the end, at the terminal nickel ions are open shell. And the experimenter reported that these two nickel ions show the antiferromagnetic interaction. So this is a so-called open shell Emacs. And very interestingly, they measure the electron conductivity of these complexes. These are experimental IV characteristics. This is a tri-metal and these are pentanickel ones. Actually, nickel complex shows a lower conductivity in compared with other metal ions, but it surely showed electron conductivity as shown here. So these complexes, we can utilize the experimental result of both magnetic property and electron conductivity. And more importantly, these are considered to be a promising candidates of single molecular wires. We have been studying about the magnetic interaction inside these molecules. For example, these are trinickel, pentanickel, and pentanickel and heptanickel ones. These are calculated exchange interaction, and these are experimental ones. And X means the actual ligand. As you can see, calculated result reproduces the experimental result. So we can conclude that electronic structures of these complexes can be reproduced by DFT calculations. Then we would like to calculate about electron conductivity of those complexes. Because these Emacs complexes are have a property of the molecular wire, and several groups examined IV characteristics of those Emacs theoretically. To my best knowledge, the first report about the theoretical calculation of the electron transpotential will be given by Professor Jin in National Taiwan University They utilized extended Huckel and estimate IV electron transportation. And after that, Professor McGrady and co-workers in Oxford University reported the IV characteristics of chromium and cobalt complexes by using an ATK program. As you can see, quantum conductivity can be reproduced by the ATK program. And we also performed the calculation of the IV characteristics of a nickel complex. Today, I would like to talk about this topic. And the interest of my study is if there is a difference in conductivity between antiferromagnetic state and the ferromagnetic state, the complex have a potential for the molecular transistor. So the purpose of this study is a theoretical calculation of the electron conductivity of the antiferromagnetic state and the ferromagnetic state. The ground state of this complex is the antiferromagnetic state. And in order to calculate or estimate the current of this complex, we used elastic green function method. And these equations, but these are very complicated. So I would like to focus on three terms. There are three important factors to consider the electron transportation of the single molecule. First one is the coupling between electrode and the molecule. Electron can be transmitted from electrode to LUMO. So the coupling between the electrode and LUMO is very important for the first step. The second one is a molecular delocalization. If the molecular orbital delocalized to the sulfur ion, this electron can be transferred easily from here to here. So the molecular orbital delocalization is quite important. The third one is the orbital energy in comparison with the Fermi energy. If, for example, if the orbital level is close to the Fermi energy, electron can be easily transmitted from electrode to the molecule. So orbital energy gap between the Fermi energy and orbital energy is quite important. And these are computation details. This is a real structure. Complex is sandwiched by the two electrodes. But the electrode is an infinite system, so it's so hard to consider the infinite electrode. So we approximate the electrode by using atomic gold diamonds. And this is a calculated model. And for the structure of the complex, we use the X-ray structure. At first, we calculate the electronic structure of whole this model. And after that, by using a calculated orbital energy and the quantum orbital and something like that, we estimate the electron transmittance by using our own computer program. Okay, I would like to move on the result. This is a calculated IV characteristics of the pentanickel complex of the ground state, antiferromagnetic state. As you can see, this is the voltage and the current. This is the IV characteristics. And as you can see, this is not linear. So it means quantum conductivity. And the curvature is quite similar to the experimental one. And the current at the 1 volt is calculated current at 1 volt is about 5.1 nanoampere. So this is also comparable to the experimental result. So we can say that this simulation is quantitatively correct. Then next, we try to calculate the electron conductivity of the ferromagnetic state. This dashed line is the calculated result of the ferromagnetic state. As you can see, the ferromagnetic state shows slightly higher conductivity in comparison with the antiferromagnetic state. The current at 1 volt is slightly larger than the antiferromagnetic state. The difference is the ratio is 1.6. The reason why ferromagnetic state shows higher conductivity can be explained by the electron correlation. In the case of the antiferromagnetic state, it has a very strong electron correlation, and the spins and the electrons localized to each side. But ferromagnetic state, the molecular orbital tends to delocalize whole the molecule. So this ferromagnetic state shows a higher electron conductivity in comparison with the antiferromagnetic state. I mean that this term is quite contribute to the whole electron conductivity of this Emax. And okay, I would like to recall the strategy of the our molecular transistor. At first, the ground state is antiferromagnetic state, and antiferromagnetic state shows a lower conductivity. On the other hand, a ferromagnetic state, it's an excited state, it shows a higher conductivity. If the molecule is in the ground state, it shows a lower conductivity. So we can say this state is off. But by irradiating or stimulate, for example, magnetic field, the molecule moves to the excited state. So it shows a higher conductivity. This state can be said on. So by the external stimuli, such as a magnetic field, we can control off and on. But if we utilize this on and off, there are two requirements. First one is a larger difference between in electron conductivity between antiferromagnetic state and ferromagnetic state. It means on-off ratio. The second one is the controllable or reasonable energy gap between antiferromagnetic state and the ferromagnetic state. If the energy gap is large, it's so hard to control between two states. Okay, again, we checked the ferromagnetic state and antiferromagnetic state of the pentanickel complex. The difference in the difference in the energy gap between antiferromagnetic state and the antiferromagnetic state and the ferromagnetic state is okay. This energy gap is quite small and we can control by the external magnetic field. However, the difference in the electron conductivity between them is quite small. The ratio is just 1.6. It's so hard to utilize as a single molecular transistor. So we have to overcome these points. Then next, we try to consider the electroconductivity of trinickel complex. This is the calculated IV characteristics of trinickel complex. The bold line is the antiferromagnetic state, and the dashed line is the ferromagnetic state. Actually, there is a large difference. This is the calculated current at 1 volt. In case of antiferromagnetic state, the current is 0.6. However, the current at 1 volt of the ferromagnetic state is more than 55. So the ratio is more than 90. So there is a big difference. So it's very good for the single molecular transistor. However, there is a big problem. Energy gap between the antiferromagnetic state and the ferromagnetic state is quite large. The energy gap is about more than 600 wave numbers. 1 Tesla is about 0.40 nanowave number. So the energy gap is quite large to control by the external magnetic field. So we have to find, or we have to overcome these problems. This is our future prospect. So problems, I would like to summarize problems at this stage. This is my homework. For the molecular transistor, we must decrease the energy gap between antiferromagnetic state and the ferromagnetic state, and or increase the difference in conductivity, I mean on-off ratio. So we have to overcome these 2 points to realize the single molecular transistor based on the spin state. Time is almost up, so I would like to summarize my talk. In my presentation, we discussed about the possibility of molecular transistor by penta and trinickel chain complex. And the conductivity of those complexes depends on the spin state, suggesting that the molecular transistor with the external stimuli. But we have to overcome several problems at this stage. Thank you very much for your kind attention.
Okay, thank you very much.
Thank
you for keeping your time. We have the 5 minutes for discussions. Any other people? Okay, so Martin, please turn on your audio, switch.
Thank you for that very interesting talk. I had a question. Can you go back a couple of slides? You had, for the large difference in conduct, yes, right here.
Yeah.
All right, you have a, if I want to make sure I understand this, you have a 670 wave number gap. How was that gap measured?
Okay, this is just a theoretical one. We
Okay.
calculate. Okay,
All right.
nifty result.
All right. And what was the magnetic field you used in the current versus in the IV curves?
At this stage, you mean a theoretical one?
Is this a theoretical IV curve?
Yeah, just a theoretical one.
All right. Did you use
okay.
Did you have an applied magnetic field in the theoretical curve? Or is that just, I know it is, you did a calculation for the ferromagnetic and antiferromagnetic state. But the problem is you have no Boltzmann population of the ferromagnetic state in an experimental situation.
You're right, you're right. At this stage, we have not examined the simulation under the external field. So we have to check how much IV characteristic curve will be changed by the external field. Thank you very much.
So I'm sorry, let me just ask one other question. So let's say you decrease that energy gap, okay? But now you run into another problem when you decrease the energy gap, because you now have a Boltzmann population over both levels. So you're always going to be limited by having a greater population of the antiferromagnetic state. Is there a way that you can actually flip their order and have use a system where you have a ferromagnetic ground state?
I think at this state it is difficult. I think antiferromagnetic state would be the ground state, even though we change the molecular structure, because the orbital how can I say, orthogonality is quite important to realize the ferromagnetic state. So we have to actually, this structure is quite important, quite interesting, because the ligand has a helical structure. So the spins in both edge have a slightly, how can I say, not distorted, have a helical structure. So there might be a slightly, I'm not sure how to explain, but there will be a still overlap still remains, even though if change the structure, there might be difficult to completely orthogonal structure.
Thank you very much. I appreciate it.
Thank you very much.
Okay, Ariona?
Yes, thank you. Thank you very much for your very nice lecture. And I have a question about the program you use to perform the calculations of electron conductivity. Is it available for other researchers, or is it free? Or
sorry, this is our own handmade program. So at this stage, we didn't open the source code. Sorry.
Okay, thank you. Thank you.
Ariona, you can ask Kitagawa Sensei to get permission to use the program.
If we can collaborate, there might be possible.
Okay, so it is possible
That's a
within
very
the
good idea.
collaborations, yes?
Yeah.
Okay, thank you.
Okay, any other questions?
Thank you very much.
Still, I can accept one question. Okay, if not, so can I ask you a very simple question? In your, the bridge site model, so there must be the adjustable parameters, non-empirical adjustable parameters, I think. Are there any such parameters?
No, at this stage, we only assume the structure, then calculate the electronic structure of the whole model.
Yeah.
So at first, we actually, we didn't introduce any empirical parameters except for the structure. Only structures we introduced from the experiment, but any other empirical parameter are not used here.
Okay, so that means totally, so the US bridge site model is very much applicable to the actual realistic systems.
At this stage, this would be the good approximation, because for example, in the quantum chemical calculation, Feynman energy can be calculated by the average of the HOMO and the LUMO energy. And this diamond model is quite good for the estimation of the Feynman energy. So at this stage, this is very simple but useful one.
Okay.
Thank you very much.
Sounds very nice. Okay, Boris?
Yes, I have one question, one point. Did your calculation using structure optimization or the position of the ion are fixed? This is a computational point, but the physical difference is that are you dealing with the polaronic states or purely electronic states? Because optimization structure implicitly include polaronic effects, and the difference in conductivity can be very, very strong.
Thank you very much. At this stage, we utilized X-ray structure. We assume the X-ray structure. I think X-ray structure is the antiferromagnetic state. So we fix the geometry to the X-ray structure. And for the optimization, it is reported that there will be several problems. For example, Professor Benner have already reported optimized result involves several errors, for example, functional sets and spin contamination or something like that. So there is so much difficult problems for the geometry optimization. So at this stage, we fix the geometry to the X-ray structure. Thank you very much.
Polaronic effect is beyond your calculation up to now.
Yes, at this stage, yes.
Thank you.
Thank you very much.
Thank you.
Okay, thank you very much, Kitagawa Sensei.
Thank you very much.
Let's move on to the next speaker. Pavel, you ready?
Yeah,
Okay.
Can you hear me?
Yeah, sure. Okay, floor is
Just a moment,
yours.
I'm starting the demonstration.
Okay, you have 20 minutes.
Okay, thank you. Hello for everyone. For today, I would like to present our scientific work about application of organic radicals for cancer treatment. Of course, the main subject of this conference is the molecular magnetism, but we of course research this part of application of stable radicals. For example, these molecules were prepared by us, and the recent work about Verdazyl radicals. But I think that this microscience research is presented by Professor Evgeny Petunin, so I think 3 or 4 speakers later. And of course, I have no reason to explain why organic stable radicals is important for molecular magnetism, but I hope that at least one person here have no knowledge about application of stable radicals in cancer therapy. So it's no secret that cancer diseases take the second place in the statistics according to World Health Organization. And photodynamic therapy, abbreviated as PDT, is one of the perspectives necessary for cancer treatment. So how it works? First, we have photosensitive molecule, PC. For example, this molecule or this one, which absorb the light and jump from the ground state to the excited state. Accumulated energy assists the transformation of triplet oxygen to the singlet oxygen, or transformation of oxygen to the some reactive oxygen species like peroxide radicals and something like that. So these active species attack the membranes, DNA, proteins, etc., which lead apoptotic or necrotic process in cells. Okay, this idea works very fine if you have enough oxygen in the cell or around cells. But there are a lot of examples when we have no enough oxygen for PDT therapy. So, okay, we lose the efficiency. There is one idea how to solve this problem. You can use some molecule with labile bonds, and using external stimuli, you can leverage these bonds to the radicals. At least one of them are active and could attack membranes and like in classical PDT. So one of the such molecules with labile bonds is alkoxyamine, which could formalize using thermal or photo or biostimuli to the alkyl radical for therapeutic application and to the nitroxide for the diagnostic application. Unfortunately, alkoxyamines absorb only from ultraviolet light. But of course, you know, ultraviolet is not so good for organisms, for normal cells, and it's a bad idea for application of such molecules for treatment. To the other hand, we have alkylated Verdazyl radicals, which could be easily decomposed to the corresponding Verdazyl radical and alkyl radical using visible light. And we, in this work, we focus on such molecules. So for the test, we apply 3 compounds, and we test cytotoxicity on the MCF7 cells. First, compound 1 demonstrated relatively high cytotoxicity under light irradiation, but in dark experiments we observed high cell viability. So it works, but compound 1 was really insoluble even in DMSO. So we transformed slightly our molecule to the molecule number 2 and tested at the same conditions this graph and this graph. Let's focus on the graph in the bottom. So under light irradiation, we observed almost linear relationship between cell viability and concentration of alkylated Verdazyl. It means that we observed dose-dependent cytotoxicity. This fact is very important for demonstration of proof of concept. Sorry. At the same time, without irradiation, we observed almost constant cell viability. I mean that without light, our compound is not cytotoxic, we think that the main part of the cells were observed during the physical and mechanistic factors due to small solubility of compound number 2. So we also tried to increase the solubility using compound 3 as agent against cancer. So we observed really strange relationship between cell viability and concentration of alkylated Verdazyl, because as you can see, there is no difference between irradiated and irradiated examples of, irradiated and not irradiated wells. It means that we think that in this situation we observe continuous formalizing of alkylated Verdazyl number 3, and both under light and without light we observe high cytotoxicity, but at least with high polymerization. Okay, to sum up the results, we can say that, okay, this concept is works, but we have to increase the solubility, of course, and of course the solubility in cells media and in condition and in organisms, and we have to increase the absorption wavelength in order to decrease cytotoxicity and transparency of the light into the organism. And okay, thank you for your kind attention, and I would like to thank the Russian Science Foundation for supporting all this research. If you have some questions.
Okay, thank you very much, Pavel. I can accept more than 5 questions. Okay, any person who want to ask the Pavel? Any questions from the audience? Can I ask you a very simple question? Your sample, I mean the compounds, is it toxic, very toxic for human beings?
Unfortunately, we did not test this compound in vivo because these compounds are insoluble in normal condition. Only we used heterogeneous condition like suspension, the micro size of the compounds.
I see. Okay. Okay. Any other questions or comment from the audience? Okay, I can see any hands raised. Okay, thank you very much, Pavel, for keeping your time. Let's move on to the next speaker. Next speaker is going to be Leoni from Barcelona.
Good morning. Can you hear me?
Yeah, I can hear you, but I couldn't see your face.
My screen is on, the camera is on. I'm here.
Sergey,
Yeah, we can see you.
can you see?
We can see, definitely.
Mr.
Both face and and voice.
Yes, we can see you.
You're not appearing yet.
No, I see the camera image, but I can't see the slides.
Ah, no, not yet. Sorry. I'm sharing my screen now.
Oh, okay, it's coming.
Okay, what about now?
Okay. Okay, you can start.
Okay, excellent.
You can have 20 minutes.
Yes. Thank you, Professor Takui.
Okay.
Thank you for the introduction. My name is Leoni Barrios. I'm working at the University of Barcelona in the group of magnetism and functional molecules. And my presentation has been entitled New Heteroleptic Supramolecular Helicates of Iron and Cobalt-2 and the Template Effect by some Encapsulated Species. So we are a group of synthetic chemists, and we build coordination compounds, but we start by constructing or designing our own organic ligands. So I did some, I classified them in different groups, in 3 different groups. The first is formed by different asymmetric organic ligands. A second is a group of symmetric organic ligands, which are, let's say, extended versions of the asymmetric ones. And we try to include some special elements in these compounds for different reasons. The first one is because we want to increase the length of the organic ligands we use, but also we want to induce in some way some chirality or some different environments for metal complexes, or for the different atoms we can coordinate. And also we want to include different functionalities like this organic moiety I show you here, and with the idea to include some optical properties. All of them has different coordination pockets, like beta diketones, the picolinate pockets, and also we want to include heteroatoms like nitrogen in order to favor the stabilization of iron-2, because we are very interested to combine spin transition with other molecular properties. And we know that these kind of pockets favor the spin transition of iron-2. So some of these molecules were very well explained by Professor Guillem Aromi last Monday. And this is a graphic summary of all these, all the compounds we synthesize and we explore and explode in different fields like quantum computing or spintronic as well. So I want to focus your attention in a family of host gas systems encapsulating different species. In 2016, we published this a paper showing a family of small helicates encapsulated small anions like bromide and chloride. And these anions are stabilized in the cavity of the helicates, showing spin transition because the formation of these hydrogen bondings. So we use this short ligand, hereafter called ligand L, and we obtain these nice compounds. And the most important feature of this family of helicates is the influence we observe from the nature of the guest encapsulated. As you can see here, the compound with bromide encapsulated present a temperature of transition lower than the compound with chloride encapsulated, and this difference is about 40 degrees. So when we change the organic ligand in order to prepare a new homoleptic helicates, for example, by using this ligand called L2, which is longer and contains this biphenyl spacer in the middle, we increase the cavity of the helicate form, and we successfully encapsulate the chromium oxalate. So the magnetic response of these compounds is beautiful, because for a first time we see a special behavior for chromium-3. As you can see here, this magnetic response of the system at low temperature comes selectively from the chromium-3, because both iron are in low spin state at low temperature. So we did the AC measurements of this nice system, and we observed for the first time the slow relaxation of the magnetization of the chromium-3. This work has been published in 2018. And this molecule was also irradiated by green light at low temperature in order to study the least effect. And as I show you here, about 30% of iron from the host changed their spins to low from low spin to high spin. So this is important because in some way it opens the possibility to external control the slow relaxation of the magnetization of this encapsulated species. So taking into account these previous results, we keep our attention on the possible encapsulation of more metal oxalates, but also the encapsulation of extended or conjugated complexes, like the case of this molecule, which is a metallotecton. And we continue our exploration in the field of encapsulation of these metal oxalates. And as this work revealed, or in this work, the authors study the metal oxalates of iron, chromium, and ruthenium as good qubit candidates for three main reasons. All of them has different spin states. Also, they show long decoherence times. But and a third important observation is all these compounds show also Rabi oscillations. So that is why these molecular compounds are good qubit candidates. So we successfully synthesize a compound of this family encapsulating ruthenium-3 oxalate. The entire characterization of these compounds is now under study, and we hope to have the full characterization soon. The iron-3 oxalate have been also successfully encapsulated in this system, showing spin transition. And part of the characterization I will show you here. The magnetic response of this compound shows that it has a gradual spin transition from low temperature to room temperature, and around 50% of the iron changing their spins at room temperature. So it's an incomplete and a gradual spin transition. These compounds usually dissolve very well in DMSO or in a mixture of 50-50 mixture of methanol and DMSO. So we did this study in solution, and we obtained a good mass spectrum. As you can see here, this compound is stable in solution, since we are observing the entire host get system encapsulating the iron-3 oxalate. We also see this fragment protonated, and also we can observe the ligand protonated and combined with some sodium atoms, which is a common pattern in this kind of compounds in solution. And also we tried the encapsulation of this metallotecton, which is the iron-3 anilate. Well, the main reason is because the central part of this molecule is quite similar to the previous metal oxalate I showed you, and we believe that the anilate can be fitted inside the cavity, And also, these metallotectons are very well known for the formation of supramolecular architectures by the formation of hydrogen bondings. So we did the synthesis using the ligand L2, and we successfully encapsulate this species. And as you can see, the annihilates are inside the cavity, and this organic moiety comes out the cavity by the formation of these windows between the strands of the helicate, which by the way, shows a spin transition. But we are working on the full characterization of this molecule right now. So to summarize, we were able to get a family of compounds encapsulating different metal oxalates, the chromium, iron, and ruthenium-free, and as a fourth member of this homoleptic helicates, we have this beautiful system encapsulating iron-free annihilate. So to move on in my presentation, now I want to show you a new family of heteroleptic compounds obtained by the template effect that this dianion has. So we selectively obtain these heteroleptic compounds when this hexaferrophosphate silicate is present in the reaction. So the heteroleptic compounds are obtained by combining two different organic ligands in size, as you can see here, the short ligand L and the ligand L3. And when we combine this organic ligand, it doesn't matter the ratio of these regions in solution. If we have this D anion present, this anion address selectively the formation of these heteroleptic compounds. So that means it has a very strong template effect. So, so far, we have synthesized 6 new compounds with this D anion encapsulated, and we have the compound with iron 2, nickel, and cobalt 2, but also we have the compounds combining the ligand L2 and the short ligand L. Today, I am able just to show preliminary results from the compound of cobalt 2. And the magnetic response gives us a high value for Kp at room temperature, which can be attributed to the spin-orbit coupling of cobalt 2. But the most remarkable aspect in this compound is that we can observe slow relaxation of the magnetization. It's important to say that we want to repeat this characterization because we want to improve the AC measurements by measuring at higher frequencies. And these compounds in general are soluble in some organic ligands, some organic solvents, sorry, and we did the fluor NMR as a part of the characterization of this compound. Why? Because we have 2 different anions present in this entire neutral complex. The guest is the hexaferrophosphate silicate, but the external counteranions to form the neutral complex are hexaferrophosphate moieties. So X-ray diffraction gave us this result, but also we can observe both counteranions or both the species present in solution. So to summarize my presentation, I remembered, well, I tried to put this in the list of the remarkable things. We successfully synthesized a new family of host gas systems encapsulating different species, chloride bromide, the entire series of oxalate of chromium, iron, and ruthenium. We encapsulated perchlorate as well. I didn't show you because of the time, but it has been successfully synthesized. And we observed a clear influence of the encapsulated species on the transition where the spin, on the temperature, sorry, where the spin transition takes place. Also, for first time, we also observe a slow relaxation of the magnetization for the chromium-3. Also, the cavity of the helical structure form offer a versatile system for encapsulation of bigger or extended molecules, as the case of iron-3 anylates. And we have a high potential or a great potential in these compounds to form multifunctional system encapsulated qubits, as the case of metal oxalates. And we observe a very strong template effect coming from the hexafluorosiliciate, sorry. And this template effect is independent of the ratio of reagents you use in the reaction, and also is independent of the method of crystallization, which usually is slow evaporation or layering in different organic solvents. And this opened the possibility to assemble, to form new coordination complexes, modulating the size of the cavity by combining two different organic ligands in size, but also this opened the possibility to play with the size of the potential guest. And to conclude, or to finish, I would like to thank to the entire group, GMMF here in Barcelona, especially Professor Guillem Aromi, Professor Jordi Garcia, and Professor Paul Lloyd for the fruitful scientific discussions. To the former members, the former member Mohana Daraushi, the current PhD student Rosa Diego, and our students Nuria Capó and Joan Cardona. And also our collaborators, Olivia Roubaud from the University of Zaragoza and Dr. Simon Titt from AALS in Berkeley for the crystallographic studies, and also for scientific discussions we got. And very recently, Dr. Valentin Novikov, who is boosting our research by the studies of these compounds in solution, which is a new topic for us. So thank you for your kind attention as well.
Okay, thank you very much for you keeping your time. We can accept more than 2 questions. Okay, Matsubei.
Thank you. Very interesting talk. Would you be so kind to show the slide number 10?
Number 10, just one second.
I apologize for asking a physical question, but it's still interesting. Yeah, I mean, the question is this nutation curve, at which temperature was it obtained? And actually, is only one ground multiplet contributing to these oscillations, or are there several multiplets? Because these are high spin systems, I mean, with iron and with chromium.
Okay, so I think these studies have been done at 5 degrees, 5 Kelvin. Okay, and but I'm not completely. Yeah, I think it was at low temperature at 5 Kelvin. Okay, and sorry, I forgot the second part of your question.
For which metal actually this curve is obtained? Is it iron?
Yeah. This Rabi oscillation is directly from the compound of ruthenium encapsulated.
Yes. Okay. Then it's spin 1/2. Okay, I understand.
Yeah. Sorry. Yeah. It's 1.5.
Okay.
Yes.
Yeah. Sorry.
Okay. Any further questions?
There are 2 more questions.
Victor?
Awesome, Kitagawa. Leoni, I'm very impressed with your presentation. Let me ask you, I'm impressed aesthetically because it's so beautiful construction. You know, what is my question? It's how you found this polynuclear compounds host gas system by chance? Or maybe you calculated in brain the history of creating of so beautiful system, and then you estimate the size of voids and directly introduced your additional metal inside the void. the history of idea how to synthesize this compound?
Well, we think about the design of these compounds because the organic ligands we have. We believe that it was possible to create these helical structures, and then we discovered the encapsulation of the small anions like bromide and chloride at the beginning, and then we think to build up this idea, and yes, it was designed from the beginning. Because of the symmetry of the organic ligands we use, we think that it's possible to fit or to accommodate different two metallic atoms and create some environment in the middle, or some cavities. So I don't know if it's well, I'm not if I'm answering well your question. But yeah, we think in the rational design of these compounds.
Because it's a little bit strange that oxalate carbonyl compound corresponds so tightly and exactly the same size like the size of your void. Thank you.
Thank you so much.
Okay, Robert, you can ask question. Robert.
Yes, thank you. I think that Valentin was the first one, but maybe after me.
Maybe next. I mean,
yes, thank you, Leoni, for a nice presentation and nice modular family of compound.
Thank you.
My question is, did you consider to enhance the cooperativity in your spin crossover systems, perhaps by some further external functionalization of the ligand, which in fact even now are quite sophisticatedly elaborated? But is it possible to do something else outside this capsule?
Yeah, we don't know. We don't know about this issue. We don't believe it exactly if it's possible or not. Not yet. So no. This is a molecular compound, so I think it's not possible to get some good interaction between the different atoms, metallic atoms in the structure. So it could be complicated. Yeah.
In fact, we know that one of the way to increase cooperativity is to make a chain or the layer, but it also could be done by the range of supramolecular interactions.
Yeah, by supramolecular interaction,
of course, it's not easy. It's
no,
not easy, no. I was just wondering if it is possible to functionalize this ligands outside the capsule.
Well, yeah, we are trying this in different ways. Okay, we are trying to functionalize the central part of the long ligands. Also putting some groups in the external rings in order to change the electronic properties, for example. But also we are thinking about the compound we put in the middle. So, for example, these iron anylates are able to form some some molecular interactions with other molecules because they are going out the cavity by the window. So I don't know, maybe by the interaction of these flat moieties with some molecules of solvent and additional molecules, we can have this cooperativity. But we need to study this. These compounds are freshly prepared, so we are very excited about the possible results we get, but still we need to study a lot of things from these compounds.
So I wish you nice fishing in the future.
Thank you very much.
Okay, Valentin, you might have several questions, but do it one.
Thank you. Beautiful chemistry as always. So my question is connected to chirality. So helicates are by definition chiral, but unless you induce somehow specific chirality, you will have a racemate. So
Yes.
would it be possible to use a strongly chiral guest, for example, some chiral derivative of this iron anilate, to induce chirality of a helicate itself? So you have exceptionally strong chiral magnet.
Yes, yeah. It's a very, very good idea. Yes. We have many ideas to apply in this synthesis of this compost, but we need to decide and put the to-do list. But yeah, this is a very, very good idea. Thanks.
Okay, thank you.
Okay. Refer to the question by Valentin. So I think we have already published the three-stranded helicate systems. Probably you know that
Yes.
paper. It's a
Yes.
kind of a model, Lloyd model for quantum computing.
Yes.
I think your system can be extended to the the lines. Thank you very much.
Yeah, thank you.
Yeah. Okay. Thank you very much for all the speaker this morning sessions. Of course, so we have a couple of the speakers after this session, and the organizer may have some announcement. Matsube. If not,
I just would like to thank you very much, Professor Takui, for chairing this session, for keeping it on time, and for all speakers for keeping their time.
Yeah, they all
that was fantastic.
Perfect. Yeah. Okay, so please come back to the 11 in Moscow time. Okay, there's a break.
Matvey, can you hear me? This is Eugenio Coronado.
My name is Sergey Evgenio.
Sergey, hi, you are here. No, I thought that also Matvey was there. Ferin was there.
Yeah, Matvey was there, but probably so he switched off his video and probably will go to have a rest.
Then I can try to
yeah. Sorry for disturbing you. I expected you have the nickname according to your given
I also suppose that. I don't understand why my nickname is the nickname of my students. Someone entered my computer and changed my nickname. And I don't know.
Okay, we will change. If you would like, we will change your nickname.
Yeah, I see that. The nickname is Samuel Mañas Valero. That means SMV. And yesterday was similar. But well, it's well, I don't care about that, but it's not my name. No problem. Okay, then in any case, I will try to share now to see if
you can do this. Yeah.
If we can see the.
Yeah, okay. So now I see it correct. It's a full screen.
It's possible to see, huh? No
yeah,
problem.
Yeah. You change slide now.
No problems. Fine. Perfect. I think that there is no problem.
So I see that you already changed your nickname. Or probably someone of co-organizers did it. Now
yeah, someone. I didn't.
Yeah. Okay, great. Now it's okay.
I'm not doing anything.
I made it.
Okay. Vyacheslav, you did it. Okay, thank you very much.
Okay, perfect. Then how are for you the meeting is fine? Is going fine?
Yeah.
I think that from the point of view of the presentations, everybody can connect. Then it's very good. But I don't like the online meetings.
We too, but it was not no other reason, no other possibilities.
No, no, I know it's impossible to travel to your place now. I would like to go, but well, I will go to Paris in a couple of weeks for another meeting, but I will go in person. But Paris is more easy than Russia.
So, and what about travels within the within the Europe? So, which country you?
It's possible.
No problem.
Yeah, it's possible to move.
No any limitations. So no, because well, as I see in any countries, this Delta virus rise up and goes down. So.
No, well, in any case, in Europe, more or less all the countries are similar. Then they don't put many problems. I have to go also to Germany. I suppose that I would not have any problem to go to Germany. The problem is if I want to travel to your place or to China or to Japan or even to the States, that this is more problematic. But to come to the rest is fine. Matvey is here. I see him also.
Good morning.
Nice to see you, Freddy.
Nice to see you. Thanks for joining us.
Yeah. No, but well, I joined you, but with another name, and now my name in the
yeah, we figure out that nickname was different, and it was not possible to see whether Professor Coronado is us or not. So.
No, but well, it's also a period in which it's not easy to connect. Then here the university is closed at this moment due to the holidays also. Then August is a month in which we are not active. Then nobody is at the university. We close the university completely in August. Then that's always like that. You know? People are used to organize meetings in August, and in Spain usually people are not participating in these meetings because they are not active. Well, for me it's fine. No problem. To move in August to other places is fine. But well, there are, if for example, the connections of people coming from my lab to the meeting, there are not so many. Well, there are because of these holidays. Then people are stopping now from the 15th of August to the end of August is the period in which you have nobody here. 15 to the end of August, the 15 to the 22, this week, the central week of August is empty. Well, it's fine. Then after the last week of August, people can come back again and are more active. Now are inactive completely. But for you, August is already a period in which the fall starts, no? The autumn already almost. Then for you, it's hot your place in summer, but in August already you start to have some activities. But here August is the hottest month and nobody's here. In Spain is in this way. Spain is stopped completely in August, in general, not only the university. But well, it's good to have meetings from time to time also. In person much better, but well, in this way then your meeting. Are you going to organize the similar meeting in 2 years or something like that or not?
Yeah, we are. We have to observe what is happening with coronavirus because actually we really would like to have in-person meeting.
No, but in 2 years should be fine, I suppose.
Yeah, I hope so. We thought that this year it should be fine. So we actually moved very far to organize in-person meeting. We even booked flights already from Novosibirsk to Nizhny Novgorod. We booked boat for welcome reception trip. Everything was done in detail, but then we had to cancel.
No, it's always a pity then in this way. I organized a meeting already, in-person meeting in May. Here in Spain, I organize every year I organize a meeting. It's a European school on molecular nanoscience. And then this year, I didn't want to organize in an online meeting. Then I asked people to come, And people were coming from, well, was not, I didn't allow 100 persons to come because the maximum amount of people I can accept is 100, but this year I accept 70 persons, students and professors, no more than 70. The students were 40, 50, and professors 20, something like that. No? But well, it was possible to organize, and it was possible to organize in person. The difference is that I had only people from Europe, from 3 countries, not from all the Europe. Then it's because it was more difficult. I had people from England, from Italy, from France in particular, but not from Germany, for example. Nobody came, and well, but well, this meeting is also a meeting for Spanish people mostly. And then there are also, because it's for a master, also a master student meeting. And then, but always I organize every year this meeting in May, and well, it's a nice meeting because there are people coming from, in particular professors coming from